First question. They want us to determine the center of the tree. And then of course we start with the procedure by removing the primary leaves. Let's make a color red. Okay, so we destroy A, D, G, H, J, only that's I, B, C, K, and P. That's the first iteration. All primary leaves are gone. We look at the graph again and you say, okay, what are the leaves now? And you know, when we remove a leaf like A, then this one automatically goes. So if we look at the tree without the already removed leaves, then E is a leaf, okay, and L is a leaf, and O is a leaf. Second iteration. Okay, we have an even smaller tree. Now F is a leaf and N is a leaf. Okay, and now we only have two vertices left, so these two vertices are the center of the tree. Question 2. Determine the centroid of the tree. Well, unfortunately we don't have a nice procedure for that one, so we just have to calculate. So let's look at all internal vertices. So let's start with E, and this E has, okay, C is weight 1, 1, 1, etc. So only the right tree is a heavy one, and this has level weight 1, 2, 3, 4, 5, 6, 7, 8. So E has weight 8 max. Okay, if we look at F, then on the right side, the right tree is one left, one less, that's 7. And on the left we have 1, 2, 3, 4, 5, 6, 7, 8. And so the max of F is also 8. If we look at J, then on the right side 1, 2, 3, 4, 5, 6, so that goes less and less. But unfortunately on the other side we get more elements, more edges. And so the left tree of J has 1, 2, 3, 4, 5, 6, 7, 8, 9. So J is 9. And you can see that when we move up to the right side and look at M and L and N, they will all become heavier with more maximum weight. So the centroid is E and F with a maximum weight of 8. Exercise 2. We have to process a graph using the depth first algorithm. So remember, depth first means using a stack. So whatever we put in first comes out last. So last one put in comes out first. We start with vertex A, it's already given in the table, and we have to choose the neighbors in alphabetical order. Okay, let's go for it. And then let's, again, just like we did in the lesson, if we've processed a vertex, let's cross it out. And if we've put it on the stack, then let's circle it. So the neighbors of A are D, B, C, and A. And we have to put them in alphabetical order, so that means B, C, D, and E. Okay, we processed the one that was put in last, so that would mean E. So we're going to process E. We cross it out, because now we've processed it, and the neighbors of E are added. And that's only the neighbors, of course, who are not processed yet. So that means G. So the stack is B, C, D with G added. Okay, we process G. That's the last one in. Cross it out. And the neighbors of G are F, C. That's the only one because E is already processed. So F and C. So we add F and C in alphabetical order. So here's first C, then F. And remember, we already had circled C. That means the old one on the stack goes out of the stack. Okay, we process F. That's this one. And we add the non-processed neighbors. That would be H, C, and D. So that would be in the order C, D, H. So this C goes. We process H. And that one has no not processed elements yet. So the stack just remains as it is. So we take out D. We process D. And we add the neighbor B. That's the only one there. So B, D, C, B, and the old version of B disappears. Okay, we take out B. Good. And then we don't need to add anything. So DC, we take out C. And I forgot here to strike out this old D. Huh? This one is gone already on this spot. So we only have C left. And that's the order. So with the depth first algorithm, alphabetical choosing, we have this situation now. Exercise 3. There are given two graphs, G1 and G2, and the question is, can you give a traversable path and traversable trail in graph 1? So what means a traversable trail? If we visit all edges of the graph exactly once. And you know we can only do that if all the vertices have an even degree, and in this case there are two with an odd degree, and that is also possible because then we have to start at one with an odd degree and end with one with an odd degree. So graph 1 we should be able to find the traversable path, and graph 2 we have an odd degree and all the others are even, should be possible as well. So let's give it a try. So let's start with graph 1. So we have to start at B or E, so let's start at B, and then from B we could go to D, we can go to A, we can go to E, C, F, B, and E. And so you see we've colored all the edges only once, and we've started at B and ended in C. This is one possibility. There are more options. Okay, if we look at the second graph, let's start at 2, and then we can go to, for instance, 1, we can go to 5, we can go to 3, 6, 2, 4, and 1, and again a traversable graph. Okay, for A there's an extra question, is it Eulerian? And then it's not Eulerian, because Eulerian means that it also has to stop and where we started. So then all the vertices should have an even degree. Exercise 4. Use Kruskal's algorithm to find a minimum spanning tree. And Kruskal's algorithm just tells us that we have to start with the smallest weighted edge, so that's this one, and then just take all other every time the smallest edge so far without making a connection, without making a cycle. So let's take this one, and we have a 3, we have a 3, we have a 3, and it's all still possible. I still don't have any connections. Okay, then we don't have any 3s left, so let's continue with a 4, still possible. This other 4 is not possible anymore, because you see it'll give a cycle with A, C, D. Okay, and then let's see if we still need vertices. No, look, we've covered all of them, so we already found a minimum spanning tree. So let's draw it in a nice tree-way fashion. So we have C connected with A, D, and F, and then we have A connected with B, and we have D connected with E. That's it. And what is the weight of that minimum spanning tree? So that's 4, 7, 10, 15. And you could also just add up the numbers here, huh? Exactly the same. A minimum spanning tree is this one, and the weight is 15. Next exercise, we have the same graph, but now we need to calculate the minimum spanning tree with the help of Prim's algorithm. That's a little bit different from Kruskal. It's a little bit easier to code, and in fact you start the same. You take the edge with the lowest weight, CF, and then you add an edge, but the edge needs to be connected to the ones you already have in your spanning tree so far. So we have this tree from CD, from DE and BA. The only one we can add is CD because that's connected. Then we have two trees left, this one and this one, but the only one connected is DE. And then in Kruskal we would have added AB. We can't do that now because it's not connected. So we have to choose a 4. And then we can take this one, DA, or CA. They're both connected. Let's just take this one. Okay, and then we still need one edge, and then again we can take this minimal one here. And then we're done, huh? All the vertices are nicely connected. And if we draw the tree, so that would be C, we go to D and F, and from D we would go to A and E, and from A we would go to B. And also minimum spanning tree, but now with the help of Prim. And the weight of this one would be 3 plus 4, 7, 10, 13, and 2 is 15. So a slightly different approach, giving us another minimum spanning tree. Exercise 6. They want us to find the shortest path from this start position and ending in this finish position with the help of Dijkstra. So you initialize everything, so the come-froms are empty and the length so far is infinite, except for the start point. So here we have, I come from nowhere and my starting length is 0. Okay, so we start from the starting point and we consider all edges coming out of this starting point. So that's the edge going to C with the length of 9, going to B with the length of 6, and going to A with the length of 2. And then Dijkstra says, okay, continue now with the shortest path so far. So that would be from the vertex A. From A we can only go to D, because we only use the unused edges, so we don't go back to our starting point. So from A we can continue to D with 2, so 2 plus 2 is 4, and we're coming from A. Consider the smallest one so far, that is D. Okay, from D we can go to I with 6, so that is 10, coming from D. And from D we can go to B with 1, so that's 4 plus 1 is 5, that's the smaller one. So we replace the 6 with 5 coming from D. And that's it. What is the smallest so far? That is B. So from B we only have to consider the track going, the edge going to E with 3. So 5 plus 3 is 8. So that would give us 8 coming from B. Okay, what's the smallest one now? That would be 9, 8, 10. That would be 8. E. From E we have a lot of possibilities. So we can go to C with 4, but that becomes larger, so we don't consider that one. From E we can go to F with 3, so that would be 11 E. From E we can go to G with 6, so that would be 14. And we can go to I with 3, so So that would be 11, and that is larger. Okay, then we have all the paths coming from E, and then we have to consider the smallest one again. We have 9, 11, 14, 10. So that's 9. C. So from C we can go to F with 4. So that would be 13. That's a bigger one. Don't take it. And that's the only one we need to consider. So that's out. Then what is the smallest one now? We still have 11, 14 and 10. So that would give us this I, 10. And then fortunately we find the path to the finished. So that would be 10 plus 6. That's 16 coming from I. That's all. Well, let's see if there's still shorter paths. We still have 11 and 14 to consider. So we go to 11, this one. And from F we can go to H with 1. And that's the only path open. So 11 plus 1 is 12. That's 12 coming from F. Then we have 14 and 12 left. So we consider H. There's 3 going to the finish. So that's 15. Oh, that's nice. We have found a smaller path. And from H we can go to G with 1. So that would be 15. But that's a larger one. No, 13, sorry. 13 coming from H. It's a smaller one. And that's it. Then we still need to consider, well, only one left, huh? This 13 one. And all the others are looked at, so that's G. And from G we can go with 4 to the finish. That's a larger one, so we don't need to consider it. So the one we found, the part we found, is length 15. And if we look at how it went, so we achieved the finish, and we came from H, and in H we came from F, and in F we came from E, and in E we came from B, and in B we came from D, and in D we came from A, and in A we came from the start. So this is our part. So we go from the start to A, from A we go to D, from D we go to B, from B we go to E, E we go to F, F we go to H, and then we reach the finish. So 2 plus 2 is 4, plus 1 is 5, plus 3 is 8, 11, 12 and 15. Okay, nice. Shortest path according to Dijkstra. Last exercise. They want us to construct a Huffman code, an optimal prefix code, with the help of the Huffman's algorithm. And the first question is just determine the frequencies of all chars. So we have an A, which happens 10 times. Then we have a space, which happens 6. We have an M, which happens 2. We have an N, which happens 4. Okay, we have a comma, which occurs 3 times. And we have a P twice. We have an L twice. And what do we missing? This is the C. It's 1. So 10, 18, 22, 25, 13. Okay, so we have 30 chars divided as given. And they want us to construct a prefix code with the help of Huffman. That means we first need to align the orders. So we have 1, 2, 2, and then we have 3, oh, another 2, 3, 4, 6, 10. That's the first step. Then we will build up the code by just combining the two smallest, that becomes 3, and placing it in the right position. So we have 2, 2, 3, 3, 4, 6, 10. 2, 2 together, place it in the right position. That would be 3, 3, 4, 6, 10. 3, 3 together. That would be 4, 4, 6, 6, 10. 4, 4 together. That would give us 6, 6, 8, 10. Then 12. That would give us 8, 10, 12. Becomes 18. 12 in front of it. And the last one is 30. Now what we need to do now is construct the tree starting with the highest number. So with 13. And at the end we hope to have leaves with frequencies corresponding with the given one. So 30, and let's make it a different color. 30 is made out of 12 and 18. So 12, 18. Then we have 18 made up of 8 and 10. Then we have 12, 6 and 6. 8, which is 4 and 4. Then we have 6, which is 3 and 3. We have a 4, which is 2, 2. And then we have a 3, which is 1, 2. And that's it. So now for every leaf we should find a corresponding jar. So let's check. So we have 10 here, and 10 would mean the A at this one. Then we have 2. Okay, let's just choose M. We have another 2. Let's choose L. Another 2. Let's choose B. Then we have this 4 here. That should be N. We have a 1. That is C. We have a 3, which is a comma. And we still have a space left. There should be a 6 somewhere. Ah, that's this one here. That's the space. Good. So now we've made a nice tree with optimum prefix. And let's just code a few as an example. So let's do it to the left with a 0 and to the right with a 1. And for instance, we could code A now would be 1, 1. And the largest one, C, because that's the one with the lowest frequency, would have 0, 0, 1, 0. That's a long code. And let's just do the space, a 6 one here, that would give us 0, 1. So in this way we have created an optimal prefix code for the sentence a man, a plan, a canal, Panama, with the commas and the spaces. Okay, what is the weight of the tree? Then we just have to add up all frequencies with the level in the tree. So we have 10 times 2, because we needed a prefix code of length 2 for A. And we have, let's just do them one by one, 6 times 2. So the A gives us the 10 times 2. I'll put the prefix, the chars in front of it, so we know we can't forget anything. Space, and then we have the M, which is 2 times 1, 2, 3, 4. Then we have the N, which is 4 times 1, 2, 3. We have the comma, which is 3 times 1, 2, 3. We have the P, which is 2 times 1, 2, 3, 4. L, 2 times 1, 2, 3, 4, and then the last one, the C, which is 1 time 1, 2, 3, 4. And if we add all of this up, so that would be 20, 32, 40, 52, 61, 61, 69, 77, 81. So the total weight would be 81. This concludes the mock exam, and the official exam will be similar to this one. So if you could make this one, feel assured it won't be a problem for you.